Let us next introduce advanced force model closures.
Welcome again to this unit on advanced force and torque closures. Let us start with what you will learn in this unit. First, I will give you an overview of the most important force closures that exist in the context of the discrete element method. Then we will go into the details of closures for the van der Waals and liquid bridge forces. These are the two dominating closures for cohesive forces, as you will see. Next, I would like that you understand the difference between sliding friction, which we have already discussed, and rolling resistance. Last, I would like to scratch on the surface of fluid-induced forces, and specifically we will do that by looking at drag force closures. In order to motivate what we're going to look at next, let us look into why we are so much interested in cohesion. Cohesive forces are forces between particles, and they have a dramatic effect on the packing of particles. What you see here on this axis is the particle volume fraction, so how densely the particles pack. Here on this axis you see the average diameter of the particles, ranging from a couple of micrometers to approximately 50 micrometers. This is data that has been published by Patelli et al. A couple of years ago. Let us now look at the experimental data. The experimental data clearly shows that with decreasing particle size, the packing density drops significantly. If we now perform DEM simulations without any cohesion model, you see that we cannot predict this trend. The packing density is independent of the particle size. However, if we include an adhesion model or an adhesion and a non-bonded van der Waals force model, you see that we can get very close to the experimental trend. Thus, in order to understand the behavior of powders with particle size of, let's say, less than 50 micrometers, we must include cohesion and adhesion models, as they are sometimes called. Let us now delve into the different interactions between particles, a part of which we have already discussed. However, now we're going to look into a more rigorous picture. First, let us look at the group of surface and field forces. To this type of forces, the van der Waals force belongs. Here, the particles interact due to dynamic dipoles that form inside of the particles. The second type of forces in this group are electrostatic forces between particles. Here we can differentiate between conducting and non-conducting materials, and we will provide an example here for the non-conducting case. The next type of forces are magnetic forces. This is more exotic. I will not discuss this in greater detail. The second big group of forces are forces due to material connections. Those material connections can be liquid, and then we speak of so-called liquid bridge forces. These connections can be made out of organic molecules, and then we talk about flocking, for example. This is a more exotic application, and not many people consider these forces in DEM simulations. Also, solid bridges, so forces due to solidified material between particles, is more an exotic application. Here, the more important topic is sintering. Again, we will not discuss these force closures in detail, as they really go into the details of sintering, for example. What you already know is that we have a third group of forces, which are contact forces. We have discussed about normal and friction forces already. Now we would like to just add one aspect, and this is rolling resistance. Another type of forces, or kind of pseudo forces that people speak of, are so-called interlocking forces. However, these are no new forces in the sense that we have to introduce a new DEM closure for that. Here, the forces originate from the specific shape of the particles. For example, the topic of non-convex particles is very hype nowadays, and people try to design these non-convex particles such that they can adjust, for example, the packing density. To sum up, we have to consider three important cohesive forces when we want to model appropriately the packing of particles. And these are very clearly the capillary forces. We're going to look here at the capillary force between two smooth spheres. This is the surface tension. We will see later how we can calculate these forces. What you see already is that these capillary forces are orders of magnitude larger than the weight of the particles for particles with a diameter of 10 microns. So 1e-5 here is 10 microns. The second important group are van der Waals forces, as you can see. And third, there are the electrostatic forces. Very important for you is the slope of these curves. For capillary and van der Waals forces, the slope of this curve is 1. Note that this is a log-log plot. A slope of 1 means that the force linearly increases with the particle diameter. As you already know, the weight of particles increases with the particle diameter to the power of 3. So the slope of this curve here, the weight of the particles, is 3. For the specific electrostatic force model that we have picked, the slope of the curve is 2. And the reason for that is that we have assumed a fixed surface charge density sigma here. Here you see a classical force closure from the book of Schubert for electrostatic forces between non-conducting particles. We don't have time to go into the details. I would just like to finalize the discussion of electrostatic forces by the obvious impact of the charge density. And this charge density is very difficult to predict and depends on many parameters. In short, it's difficult and no one has found the ultimate solution to predict electrostatic forces. Next, there is an important question. What about roughness? Does it matter whether particles are smooth or have surface asperities, so are rough? Let us therefore look at this idealized picture of rough particles. Here we have particles with a main diameter dp and a roughness diameter d rough. If we now consider the classical force models for van der Waals forces and capillary forces that you will see in the next parts of this unit, you will see that the surface roughness has a humongous effect on the van der Waals forces. You see a dramatic drop of the forces, a sweet spot where we have a minimum van der Waals force, and then an increase of the force. The increase of this force can be explained by the increasing van der Waals force between those two half spheres on the surface of these particles. Of course, the decrease is caused by the increased distance between the two main bodies. You will see this later. For the capillary force, you see an interesting behavior. You see that depending on the bridge volume, V star here is nothing else as a dimensionless bridge volume that you will see later, has an important effect on when the surface roughness matters. So for a large bridge volume V star, you see that for a very large range of the roughness diameter, there is almost no effect on the capillary force. These are the important things for cohesion forces. I hope you like this part, and next we go into the details of these cohesion force closures.